Basic principle of CT. Introduction. CT scanner. CT scanner is a computer-assisted tomography which scans an object in cross-sectional format in defined thickness that's free from superimposition of an overlying structure by using a computerized mathematical reconstruction process. CT equals computed tomography. The word tomography is derived from a Greek word tomos, slice, and graphia, describing. Tomos, slice, graphia, describing. History of the tomography. First approach done by mathematician J. Radon. He uses the infinite sets of projection to reconstruct the 2D and 3D image of internal structure with the use of complex mathematics in 1917. The work in this field is continued by Braswell, a radio astronomer who made solar map from multiple ray projection in 1956, and again by Oldendorf in 1961, and Alan Cormack in 1963 made his computer-assisted tomography laboratory model. Kuhn and Edward in 1968 made a type of scanner used in nuclear medicine. But this technique of imaging was embedded in the diagnostic radiology by Godfrey Hounsfield, and senior scientist at EMI Limited in 1972 made a EMI scanner. In 1979, Alan M. Cormack and Hounsfield were awarded the Nobel Prize combinedly for the development of computer-assisted tomography. Principle behind CT. The basic principle of CT is that the internal structure of an object can be reconstructed from multiple projections of the object taken. The tomographic image is a 2D cross-sectional image corresponds to a 3D section of the object. System components of CT. A CT system comprises several components. These basically includes console room and the examination room. Inside the console room there is a console operator which includes the graphic monitor, keyboard, mouse, and computers. In the examination room there are the scanning units and the control room. Scanning unit comprises the gantry, and the gantry comprises the X-ray tube generators, detector array, detector, data acquisition system, slip rings, and the patient table and couch. Control room includes the AC plant and the UPS system. Control room. Graphic monitor provides to view the reconstructed image in 2D, the analog image, and embed image manipulation techniques such as zooming, panning, control contrast and brightness, image analysis techniques, and etc. Keyboard and mouse helps to enter the patient data and quick reference guidance. Computer links the CT technologist and other components of the imaging system. It helps to reconstruct the CT image from the millions of mathematical operations required to digitize and reconstruct the raw data. The CT imaging system requires a large computing capacity, is designed to control the data acquisitions, processing, display, retrieval, and the storage. Calculates the attenuation of the individual voxel using special algorithms. The microprocessor and the primary memory are used as the heart of the computer. These determine the reconstruction time and influence the efficiency of the examination. Array processor is used instead of the microprocessor these days because they do many calculations simultaneously and fastly than the microprocessors. Generators. In CT generators, the three-phase power for efficient production of X-rays. In the past, generators were based on 50 or 60 Hz voltage frequency, were bulky and located in a corner of the examination room, X-ray room, and a long high-tension cable connected the generator to the X-ray tube in the gantry. Modern CT scanners use high-frequency generators which are small, compact, and more efficient and located inside the gantry. In generators of the CT scanner, low voltage, low frequency alternating current from the main power supply is converted into high frequency and high voltage 500 to 25,000 Hz direct current of almost constant voltage is supplied to the X-ray tube. The voltage ripple is less than 1% compared to 4% from the three-phase dual pulse generators. Current city generators have maximum power rating of about 40 to 80 kilowatt that allows kVp in the range of 80 to 140 kVp and tube current in the range of 100 to 800 mA. Nowadays, in all modern city scanners possesses constant potential generator which houses inside the gantry and rotate along with the X-ray tube. Specifications: power 40 to 80 kilowatt, kVp range of 80, 100, 120, 130 and 140 mA, ranges up to 800 mA, and the mA modulation is also available. mA maximum coverage of acquisition time is the 120 seconds. Note: to maximize the imaging efficiency, a constant potential supply is required and the kVp must be stable. Since fluctuations tend to cause image artifacts, three-phase dual pulse middle or high frequency output satisfy this need. Typically, an output of 80 to 150 kVp is required. X-ray tube. CT require longer exposure time at higher kVp than needed for general radiography. Early generator CT scanners use only oil-cooled stationary anode, relatively large 2 x 16 mm focal spot operated at 120 kVp and 30 mA, heavily filtered X-ray tube. Nowadays, the CT tubes are a heavy-duty rotating anode with higher thermal capacity and smaller focal spot of 0.6 to 1.2 mm, which are air-cooled with current value up to 800 mA. Borosilicate glass envelope has been replaced with a metallic envelope, alloy of chromium and iodine, and a ceramic insulators of aluminum oxide. Anode disc is made up of compound materials consisting of tungsten rhenium focal track brazed to graphite base with disc diameter up to 200 mm compared to 75 to 160 mm. Anode speed is increased up to 12,000 rotations per minute by having liquid bearing technology for smooth rotation of discs. Example: gallium-based liquid metal alloy. Air-cooled rotating anode having smaller focal spot 0.6 mm, heat loading capacity 3.5 MHU million heat units, and higher heat dissipation efficiency. Oil water-cooled tube were introduced having high heat dissipation efficiency. Some CT tubes are grid controlled for pulse radiation to reduce patient radiation dose. It should supply monochromatic X-ray beam for accurate image reconstruction. Tube housing. The material of the tube housing is the borosilicate and metal ceramic having heat storage capacity of 1.2 to 8.3 MHU, and oil is the distilled oil. Anode diameter of the anode is the 200 mm, weight is 2000 gram, heat dissipation rate 1 MHU per minute, anode angle 10 to 12 degree, focal spot 0.6 to 1.6 mm, rotation 9000 to 12000 rpm. Material: tungsten, rhenium, molybdenum and graphite. Cathode material: tungsten type dual focus. Detectors. CT detectors capture the transmitted radiation beam from the patient, first converted it into the light photons and then into the amplified electrical signal, which are subsequently converted by analog to digital converter into binary coded information for onward transmission to the computer system for further processing and image reconstruction. Detector is a crystal or ionizing gas that when struck by an X-ray photon produces light or electrical energy. The term detector array is used to describe the total number of detectors that a CT system utilizes for collecting the attenuated information. Third generation CT imaging system employed 800 to 1000 detectors, while fourth generation includes 4000 to 5000 individual detectors in a detector array. Ideal features of the detector. Detector must be capable of responding with extreme speed to a signal without lag, must quickly discard the signal and prepare for the next. It should have high detected quantum efficiency, high absorption efficiency. It should be more than 90%. Ideally, it is 100%. Higher conversion efficiency, good homogeneity, purity of more than 99.99%, small afterglow. It should be less than 0.01%. 100 milliseconds after the end of the irradiation. Fast response time. Response time refers to the length of time it takes for a detector to review and discard signal, which influences image contrast, and it should be less than 0.1% difference. high packing density, which influence the resolution. Wide dynamic range refers to the detector ability to receive wide range of X-ray intensities from low to high and convert them into proportional output signal, which is dependent on the accuracy and precision of the ADC. High stability. It is controlled by how often the detectors must be recalibrated to meet quality control standard. Cost as minimum as possible and easily available. The efficiency of X-ray detector array reduces the patient dose, allows faster scanning time, and improves image quality by increasing the SNR. There are mainly two types of detector system: gas ionization detectors and scintillation crystal detectors. Gas ionization detector, a small multi-chamber inert xenon gas detector, is the gas ionization detector, and scintillation detector includes multiple scintillation detectors with photomultiplier tubes or multiple scintillation detectors with photodiodes. Gas ionization detectors. Gas field ionization detectors consist of the inert xenon gas chambers, which is individually separated by tungsten plates known as metal septa, enclosed by a relatively thick ceramic substrate material. The entire detector array is hermetically sealed and filled with an inert gas of high atomic number, that is xenon or xenon krypton mixture, under high pressure of around 25 to 30 atmosphere to increase the number of gas molecules available for ionization, which improves the X-ray detection efficiency. The complete detector array is subdivided using electrode plates into a large number of chambers up to 1000. Each one shares the same gas volume, minimizing variation in sensitivity between the chambers. As X-ray interacts with the xenon gas atoms, ionization takes place, and then the electric field within the plates causes the charged ions to move towards the electrodes, where the electronic charge is collected as the electric current. The electric signal is amplified and then digitized, which numerical value is directly proportional to the X-ray intensity striking the detector. Used mainly in rotate systems because of long linear structures. Gas chamber size is wide 1 to 2 width of 1 to 2 mm, height of 10 mm, and depth of 10 cm. Gas inert gas xenon of atomic number 54 or xenon krypton mixture. Anode side plate made of copper. Cathode side plate made of tantalum. Pressure approximately 25 atmosphere up to 30 atmosphere. No afterglow, very fast response. This is the schematic diagram of two adjacent ionization chambers of a xenon gas high pressure detector array. Here the xenon gas which are positively charged are attracted towards the cathode, and the electrons which are negatively charged are attracted towards the anode, which is the positive electrode. Advantages of gas ionization detectors. It is cheap and easily available. It has constant sensitivity in both long and short terms, indifference to change in ambient temperature and humidity, wide dynamic range, rapid response without afterglow. It is less dependent on stable high voltage supplies, is inherently uniform, and provides in-well collimation as an added bonus. It shows better thermal stability than scintillation detectors. Disadvantages: their quantum detection efficiency is only less than 50%, which is about 50% of the solid-state scintillation crystal detectors. The xenon gas has to be maintained at high pressure to increase detection efficiency and heighten uniformity of response to exposure. Solid-state detectors. It is known as scintillation crystal detector. It is composed of a scintillator coupled tightly with either a photomultiplier tube or photodiodes. The scintillator emits visible light when it is struck by X-ray, just as in an X-ray intensifying screen. The light emitted by the scintillator reaches either on photomultiplier tube or photodiodes, which is an electronic device that converts light photons into an electrical signal proportional to the light intensity. In the past, earlier series scanners, that is first and second generation, used sodium iodide as crystal doped with as detector doped with thallium coupled with photomultiplier tubes and X-ray as coupled with photomultiplier tubes. The photomultiplier tubes could not provide the packing density that was necessary with fan beam geometry, required a power supply for its photomultiplier tube, which make the detector bulky. So because of poor packing density, higher afterglow and limited dynamic range, it was quickly replaced by silicon photodiodes. Nowadays, commonly scintillation coupled with solid-state photodiode detectors are used, and the scintillation material used with photodiodes are ceramic material made of high purity rare earth oxides based on doped rare earth compounds such as yttrium, gadolinium oxysulfide, GSO, ultrafast ceramic detectors, etc. Detector elements convert the absorbed X-ray photons into visible light. The light is then detected by silicon photodiode. The resulting electric current is amplified. The silicon photodiode then converts the light into electrical current, and the resulting electrical current is amplified and converted into a digital signal. Advantages of photodiodes: they convert the light photons into electrical signal and are smaller in size, greater stability, cheaper, and do not require a power supply and are equally efficient as other CT detectors. The packing density, DQE, QAE, CE, and effective atomic number of scintillators are substantially higher than those of pressurized xenon gas, so that solid-state detectors typically have better X-ray absorption efficiency. Their increased efficiency can result in less X-ray tube loading, reduced image noise, and reduced patient dose. The top surface of the solid-state CT detectors is essentially flat, and therefore it is capable of X-ray detection over a wide range of angles, unlike the xenon detectors. Disadvantage is relatively long afterglow following the detection of the X-ray photon, which deteriorates the spatial resolution. Stable output signal depends on a very stable high voltage supply. Multi-detector uniformity of response is difficult to maintain. It may be less stable in the long term due to lack of uniformity in the crystal's response, persistence of light emission after irradiation has ceased, afterglow, and aging. Long-term efficiency is less as they require time-to-time calibration. Sequential CT: a cross-sectional image is produced by scanning a transverse slice of the body from different angular positions, while the tube and the detector rotate 360 degrees around the patient, with the table being stationary. The image is reconstructed from the resulting projection data. Helical, spiral, or volume CT. Spiral CT uses a different scanning principle. Unlike in sequential CT, the patient on the table is moved continuously through the scan field in the z direction, while the tube performs the multiple 360-degree rotations in the same direction. It is the modification of third generation CT that uses the slip ring technology and made possible of volumetric data acquisitions. In this generation, several advancements are applied, such as X-ray tube with massive thermal loading capacities, high precision table stepping motors, faster acquisition and reconstruction process. The X-ray traces a spiral around the body and produces a data volume. This volume is created from a multitude of 3D picture element voxel. The table movement in the z direction during the acquisition will naturally generate inconsistent set of data, causing every image reconstructed directly from a volume data set. Thus, it is possible to reconstruct individual slices from a large data volume by overlapping the reconstruction as often as required. This figure shows the spiral scanning. In spiral scanning, we have to perform interpolation to form the image from the data, helical data acquired. Advantages: short scan times resulting in fewer motion artifacts and low contrast requirement, large anatomical coverage in a single breath hold in the helical scan, improve lesion detection due capture of real-time contrast optic of the lesion, reduce partial volume artifact, additional diagnostic information due to improved resolution, thinner slices are possible in helical scan, and the 3D visualization in routine operation, improved patient throughput and improved patient comfort, improved z-axis resolution, that is the temporal resolution, capable to scan in both axial as well as in helical mode, increased image noise, reduced spatial resolution. Reconstruction time is longer due to more data accumulation in a shorter time, increased higher patient dose. Digital image components pixel. It is a 2D, that is X and Y picture element that makes up the matrix. Each pixel represents a numeric value, that is linear attenuation coefficient, and is the building block of the matrix of an image. A monochromatic pixel can have two values, black or white, that is 1 or 0. Pixel equals FOB divided by matrix size. Voxel, it is a three-dimensional element of anatomy represented by the 2D, that is X and Y. Pixel in smallest distinguishable box shaped part, that is the volume of tissue of the patient. Voxel size equals pixel size multiplied by the slice thickness. So in pixel size, pixel element is the 2D representation and the voxel element is the 3D representation. Tomographic acquisition, ray, a single transmission measurement through the patient made by single detector at a given moment in a time is called as ray. A ray is just a single projection, and the projection is a series of rays that passes through the patient at same orientation called a projection or view. Ray is the component of a projection, and the projection is a series of rays. Basically, in CT image acquisition, parallel beam geometry and fan beam geometry are used. Nowadays, all modern CT scanners used fan beam geometry in the data acquisition and reconstruction process. CT image is made up of many projection or views which consist of many scan lines or rays. First and second generation scanners used 28,800 and 3,24,000 data points respectively. State-of-the-art scanner may acquire about 8 lakh data points, 1,000 views with 800 rays per view. Modern 512 plus 512 CT image contains about 2 lakh and 5,000 image pixels. Formation of a CT image. A single transmission measurement to the patient made by a single detector at a given moment in time is called as ray, which I have already described, and the projection is a series of rays. Sinogram. The data acquired from one CT slice can be displayed before reconstruction. This type of display is called sinogram. Rays are plotted horizontally and views are shown on a vertical axis. During 360-degree CT acquisition of a particular object, the position of the ray corresponding to that object varies sinusoidally as a function of the view angle. The number of rays used to reconstruct a CT image has a profound influence on the radial component of spatial resolution, and the number of views affect the circumferential component of the resolution. CT image of a object reconstructed with different number of rays so that reducing the ray sampling results in low resolution and blurred image. CT image of the object reconstructed with differing number of views so that the effect of using too few angular views, view aliasing, which decrease the circumferential resolution. Reconstruction, increasing the number of rays, increased spatial resolution. Reconstruction, increasing the number of views, increased the circumferential resolution. Acquisition and image reconstruction process. An X-ray beam which is transmitted through an tissue element having linear attenuation coefficient mu of thickness x given by n equals n naught e minus mu x, where n naught is the number of individual initial X-ray photons and n is the number of transmitted photons. E is the natural exponent, and the value of n naught, n and x can be measured, but only the unknown is the linear attenuation coefficient mu. For n tissue voxel, the acquisition equation becomes n equals n naught e minus mu n plus mu 2 plus mu 3 plus up to mu n and x, where mu 1 plus mu 2 plus mu 3 up to mu n are the linear attenuation coefficient of 1, 2, 3, 4 up to nth voxel. By solving this equation, the value of mu 1 plus mu 2 plus mu 3 up to mu n of individual voxel can be calculated. Exponential attenuation of rays. So the linear attenuation coefficient are just added. CT number. The relative attenuation coefficient is normally expressed in Hounsfield unit, which are also known as CT number. Therefore, each tissue element voxel is assigned by a CT number. The relation between linear attenuation coefficient and CT number is given by HU equals K multiplied by mu T minus mu W by mu W, where K equals 1000, a constant factor which determines the contrast scale. Mu T and mu W are the linear coefficient of tissue element and water. Note the CT number HU value generated by a CT scanner are approximate and depends upon the KVP and the filtration. Correction CT for heterochromatic nature of beam, weighting factor to compensate the difference between the size and shape of the scanning beam and the picture matrix. For heterochromatic nature of beam, 70 kV monochromatic, and when becomes heterochromatic, it decreases with increasing the thickness. Linear attenuation coefficient decreases with increasing the thickness. Correction for the weighting factor. Here the weighting factor is 1 for the right hand side of the particle projections, and for oblique projections the weighting factor is less than 1. So the pipeline principle of image reconstruction is data acquisition. Data are acquired in gantry, and those data are passed into the analog and digital converter, and they are pre-processed by 2D Fourier analysis and then reformatted and then convolved by Lac filter or Chape-Logan filter or Hamming filter, then are carried on to the image reconstruction processes by back projection or iterative or analytical, and then again are converted from digital into analog form, which are displayed and again can be post-processed by, that is, windowing and ROI and linear and volume measurement, SSD, MPR, MIP, VRT, CTA, etc., and again can be image archived and recordings. So the data acquisition systems, the signal from each radiation detector of a multi-slice CT scanner is connected to a computer controlled electronic amplifiers and switching devices called as data acquisition systems. It connects the detector combinations for signal summation. From detector passed into the pre-amplifier, from pre-amplifier into logarithmic amplifier, and then into analog to digital converter. In pre-amplifier increases the signal strength for lateral processing, and logarithmic amplifier compresses the dynamic range, converts the transmission intensity into attenuation data. Pre-processing digitize data from digital to analog system, transmitted to the image processor, At this stage, the images are reconstructed by means of pipeline principle consisting of preprocessing and convolution. It includes all the corrections taken to prepare the measured data for recon. Example correction for current dose, output calibration, channel correction, and beam hardening errors. Algorithms for image reconstruction process. An algorithm is a mathematical method for solving a problem. There are three mathematical methods of image reconstruction: algorithm, iterative back projection, and analytical. Analytical can again be filter back projection and Fourier transformation. Iterative method. It was originally method for image reconstruction used by John Hounsfield, that is Godfrey Hounsfield, in the first CT machine. An iterative reconstruction starts with an assumption like all points, that is pixels in the matrix, have same value, and compare this assumption with measured values, and then repeat the process in a series until the assumed and the measured values are same or within the acceptable limits. This method, also known as series expansion or successive approximations or correction technique, and it is done by three ways: simultaneous reconstruction, ray by ray correction, and point correction. So this shows the iterative ray by ray correction of 4 elements. Advantages: with incomplete data, iterative method are better choices of image reconstruction. Better imaging is in limited number of projection, better than the filter back projection in metal artifact. Disadvantage: it is not used in commercial CT scanners because the iteration cannot be started until all of the projection data have been acquired before image reconstruction can begin. So it causes a delay in image reconstruction process, which takes a considerable amount of computer time that makes examination slow. It also suffers from rounding errors, that is 0.95 tends to be 1.0, which gives imprecise CT values. Simple back projection. It is also known as summation method or the linear supposition method. In this method, each X-ray transmission path through the body is divided into equally spaced elements, and each element is assumed to contribute equally to the total attenuation along the X-ray path. By assuming the attenuation for each element over all X-ray paths that intersect the element at different angular orientation, a final summed attenuation coefficient is determined for each element. When this coefficient is combined with the summed coefficient for all other elements in the anatomic section is scanned by the X-ray beam, a composite image of attenuation coefficient is obtained. So here the X-ray tube and the X-ray detector array lying perpendicular to each other, and the middle is the object, and the X-ray pass through the object, and that is the projection profile formed on the detector array. Curvilinear integral of absorption coefficient regarding y-axis, and in the reconstruction field we can back project multiple times, which form the final image of the object, but it causes some blurring, so the number of projections must be increased to decrease the blurring. So from back projection, blurring is the major artifact. Advantages of simple back projection: it is a process through which modern image reconstruction technique become possible. Although the simple back projection approach to reconstruction algorithms is straightforward, it is not used by any commercial CT scanners due to a high blurring effect and in images of sharp features in the object, that is not sharp and clear image. Analytical. Current computer commercial use this method. A mathematical technique known as convolution or filtering technique employs a spatial filter for Removing the blurring artifacts. Two types: filter back projection and Fourier filtering. Filter back projection, similar to back projection except that the image is filtered or modified to exactly counterbalance the density, which causes blurring in simple back projection. The mathematical filtering step involves convolving the projection data with a convolution kernel, faster as compared than iterative. Both are accurate if projection data is complete. Convolution filter refers to a mathematical filtering of the data designed to change the appearance of the image. A high-frequency convolution filter suppresses high-frequency signals, causing the image to have a smoothing appearance and possible improvement in contrast resolution. A low-frequency convolution filter suppresses the low-frequency signal, resulting in edge enhancement and improvement of spatial resolution. Steps in filter back projection. All projection profiles are obtained. The logarithm of data is obtained. The logarithmic values are multiplied by digital filters. Filter profiles are back projected. The filter projections are summed and the negative and positive components are cancelled. Projection data reconstruction filter. Filtered projection data. Multidirectional back projection. Convolution. It is a mathematical filtering process of projected data by the mathematical filter kernel to reduce the blurring effect of the projection. The filter may be a Lac filter, Sepp-Logan filter, or Hamming filter. Another name for Lac filter is the Ram-Lac filter, after the name of the engineers Ramchandra and Lakshmi Narayan. Ideal reconstruction filter in the absence of noise is the Lac filter. Sepp-Logan filter incorporates some roll-off at high frequency. Reduction in amplitude at high frequency has a profound influence in terms of reducing high frequency noise in the final CD image. Hamming filter, it has even more pronounced high frequency roll-off with better high frequency noise suppression. The red one is the unfiltered one and the yellow one is the filtered profile. So the back projected image when filtered forms the filtered image with better resolution and no blurring at all. Fourier analysis. The basis of the Fourier analysis is that any function of time or space can be represented by sum of various frequencies and amplitudes of sine and cosine waves. The Fourier transform is used to convert a function expressed in the spatial domain, millimeters, into the spatial frequency domain, cycles per milliliter. The inverse Fourier transform is used to convert back, also used in MRI. Image reconstruction in spatial CD. Reconstruction of spiral CD image is the same as those for conventional CD except for the interpolation. Interpolation is the computation method of an unknown value using known values on the either side. A transverse planar image can be reconstructed at any position along the axis of the patient, that is z-axis. Data interpolation is performed by a special computer program called an interpolation algorithm. Interpolation algorithm during a spiral or helical CD image data are received continuously, but when an image is reconstructed, the plane of image doesn't contain enough data for image reconstruction. So the data needed for image reconstruction estimated by a special computation method known as interpolation algorithm, which means the estimation of value between two known values. The ability to reconstruct an image at any z-axis position is due to interpolation. Reconstruction of an image at any z-axis position is possible because of a mathematical process called interpolation. Interpolation algorithm can perform interpolation as well as extrapolation. as earlier mentioned, is the estimation of the values between two known values, and extrapolation is the estimation of the value beyond the range of known values. Interpolation algorithms can be 360-degree linear interpolation or 180-degree linear interpolation. The plane of reconstructed image interpolated from the data acquired in one revolution apart. Interpolation of the value separated by 180 degree, half a revolution of the X-ray tube. 360-degree linear interpolation blurred in the reformatted image. 180-degree results in improved z-axis resolution and greatly improved reformatted image. 180-degree linear interpolation. Interpolation of the values separated by 180 degree, half a revolution of the X-ray tube, results in improved z-axis resolution and greatly improved reformatted image. Results thinner slice than 360-degree interpolation. Results more noise image than 360-degree. 20% higher noise than conventional CD. Allows scanning at higher pitch, less broadened sensitivity profile. In 360-degree, the plane of reconstructed image interpolated from data acquired in one revolution apart, blurring in the reformatted image, thicker slice than 180-degree, less noisier than 180-degree, 20% less noise than conventional CD, allows scanning at lower pitch than 180-degree, broadened sensitivity profile. Z-axis resolution is low in 360-degree, high in 180-degree. Slice sensitivity profile is broadened in 360-degree, narrow in 180-degree. Spatial resolution low in 360-degree, high in 180-degree. Noise is high in 360-degree, low in 180-degree. Pitch allows scanning pitch greater than 1 in 360-degree, allow scanning pitch less or equal to 1 in 180-degree. Reconstruction time. The time from end of imaging, end of data collection to image appearance is the reconstruction time. Reconstruction time of 1 second and less are common in all clinical CT scanners used today. Image reconstruction time is determined by ADC rate, CPU, amount of data collected, and convolution filter chosen. These are the references of today's presentation. Thank you.